what I'll talk about today is one particular application where under certain circumstances, you end up with a problem that's related to matrix completion. Right? So I'll just start with a brief introduction to X-ray computed tomography. So the typical situation is that you have a number of projection images, so normal X-ray images of some object. And so you have images like this from many different angles. So you rotate the object or you rotate the scanner around the object and acquire images like this. Then you typically also record what's called a flat field image that just records the response of the detector and the source intensity of the X-ray source. And then you normalize your projection images so that they look something like this. And this is something that also goes on if you take a picture with your camera in your smartphone. Then there's a correction, a flat field correction, because you may have that in the corners of your image, the illumination is very different from the center, and you can compensate by that by correcting with this flat field image right here. So then you have what's called a transmission image. So this is, so white here means that you have no absorption basically. And then the dark colors here is high absorption. So this gives you sort of a photon survival probability. So the values over here are between 0 and 1. And then in computed tomography, the task is to take what's called a sinogram. So if I take out one slice here, a horizontal slice of each of these images and put them as columns down here in this matrix down here, then I have what's called a transmission sinogram. And the task is then to map that to a image of the interior of the object. So here it's an attenuation image that shows how much the different parts of the object attenuates the X-ray beam. Right? So this is used in material science. It's used in medical imaging and many other applications. So normally this is quite easy, and there's not really. So let me just introduce the model here. So the model is based on Lambert-Beer's law, which relates the ratio of the incoming intensity of some X-ray source to the outgoing intensity here through a line integral over some attenuation function here. This is the spatial attenuation as a function here of the position. And so these are line integrals. So we have to compute a line integral along this ray right here. And so the log of this ratio is a linear function of this function mu here. So we can introduce some discretization, some pixel grid, for example, and then we can, based on our measurements and our known intensity, we can set up a system of linear equations. And typically it's the situation that we have some kind of noise as well. So we have observations that include the line integrals, but also some noise. And we do this in a systematic way by setting up, for example, in what's called parallel beam measurement geometry. You have a source and then an incoming beam, and you can think of the rays here as being parallel, and then you have a detector. Then you rotate the detector and the source, acquire a new projection, and you do that for many different angles, and then that gives you this sinogram that you used for the, so basically the vector B here is a vectorization of this sinogram here, the measurements that are used to compute the image. So there are many different methods for then computing a reconstruction. There are analytic methods that basically are based on the fact that the measurement model is a radon transformation. So it's called the inverse radon transformation. Then when you use these analytic methods, there's oh, excuse me, there's a particular variant of this that's called filtered back projection, and another very similar method here called grid reg, which works by doing essentially regridding in the Fourier domain, and that has the advantage that you can for high signal to noise ratios, you can really do almost real-time reconstruction for high-speed experiments. So you can do dynamic CT with a method that's sufficiently fast. So the other class of methods, that's the algebraic methods that basically treat this as a system of equations that you then solve. Kaczmar's method is one method that's closely related to a stochastic gradient method or incremental gradient methods. And there are various other methods that basically solve a set of linear equations, and some of them also apply to the least squares case, where you somehow minimize the difference between AU and B in some weighted norm. And then, of course, that can be extended to variation of methods, for example, maximum likelihood estimation or a maximum a posteriori estimation, where you then minimize some, for example, again, weighted least squares term and some regularization or prior information on your attenuation image here. So now the issue is if we have noisy X-ray images, and this may happen if we have low dose experiments. So for example, in medical CT, you're interested in doing experiments with as low a dose as possible to avoid exposing the patient to radiation or more radiation than necessary. It also happens, for example, if you have fast acquisition, you want to do dynamic studies of some moving object, for example. Then you also need a very short exposure time, and then that means you get noisy projections. And so here's a real data set from Oregon National Lab. And these are the projection images. This is this flat field image. And here are the normalized images. So let's try to zoom in, and you can see it sort of looks kind of grainy over here. You have a little spot here, and it's also over here. And that is something that's on the detector, and it's gone over here in the transmission image, but it's still quite noisy. So now if we try to compute a reconstruction using at one of these standard methods, you get something that looks like this, and we can blow it up a little bit. And I don't know if this is visible over Zoom, but you may be able to see a ring-like structure in the noise. For example, here. And this is really something that makes it quite difficult to use these images for the intended purpose. What you can then do is that you can say, well, if this is really a 3D problem, you can start to take the average over several slices. So if I start averaging slices and reducing the resolution in one of the directions, then we start to see that we can see some kind of structure here, but we also get more and more blur in the image because we're really starting to reduce the resolution in one direction here. So the reason for these rings in the reconstruction can be explained by the fact that you have stripes. This is really hard to see here, but there's a stripe through the image right here, and you can see that in the blow up here. And after going through this reconstruction step, that turns into a ring in the reconstruction, right? So if you have somehow a stripe in your sinogram, that gives you a ring. And the magnitude of that ring depends on so this is a radial profile of just the ring right here. And depending on where this stripe appears on your detector, so the detector is in this direction right here. If it's in the center of the detector, then the magnitude will be large. And the further away you go from the center, the smaller the magnitude, but also the larger the circle in some sense, right? So there's some energy here in this this stripe here that has to be in some way placed in a circle, and the smaller the circle, the larger the magnitude. Right. So this is something that you can analyze, or you can derive analytically what this looks like. But of course, this doesn't really explain why you have these stripes in the sinogram. And the reason for this is that you typically, well, before I move on, let me mention here that the reason is that when you do this step by normalizing by the flat field, that's basically taking all the columns here and dividing by element-wise by some other vector. So you're making a systematic error, and it's after or basically you take the ratio and then you take the log. So an error in the flat field will turn into a stripe in the sinogram. Right. So if you don't have a very accurate flat field, you're going to end up with rings in your reconstruction. So now the ways that people have addressed this problem is by either pre-processing. So this means removing stripes from the sinogram, or post-reconstruction processing. So that means removing rings from the reconstruction. Or as part of the reconstruction where you model then that you have some kind of systematic error, which shows up here as a Kronecker product, where this then is an additional variable that is included in this model. And this is then motivated by a measurement model where you have the same Lambert-Beer law, but instead of having just a single intensity here, that's the same across every pixel, we include a vector here of the detector efficiency, and also takes into account that you may have what's called a cone beam. So for example, near the edge of the detector, the illumination may be, or the intensity may be lower than at the center, right? And you can model that by including such a vector right here. And then you can apply this same transformation to turn it into a linear system of equations. And then what you get is something like let's say we can do a decomposition here as a noise-free data. Of course, we can't really get that in reality, but you can write it as the noise-free data plus some random noise and some structured noise here that comes from these stripes. And it turns out here that you can affect the noise variance here, because we can model this as being a normal variable that depends on the number of flat field samples. So the variance is inversely proportional to the number of flat field samples, but also inversely proportional to the intensity of the beam, right? So if we have a high signal to noise ratio, high intensity, and we have a lot of flat field samples, then we can ignore that, and it's not really a problem. So another way to deal with this is by using a technique that is to basically shift the detector or the object at the time you do the acquisition. So then the stripes will appear less systematic. And what will happen then is that, so using this reconstruction method here called filter back projection, we can apply it to each of these terms here. This will give you the noise-free reconstruction here of some object. This is just the noise term. So this will also be the noise term of your reconstruction, and the stripes come from the last term right here. But by using this this detector shifts at the time of acquisition, you can sort of smear out this. It doesn't really take care of it. It doesn't remove it completely, but it smears it out. And as you can see here, you get low frequency variations in the component here of the reconstruction here. So this is additive because this is essentially a linear reconstruction method. So it's you have to add these components to get your reconstruction. So this talk is about jointly estimating the intensity and the detector response and the attenuation image. So we will now try to get around this by including not only the detector response here and the intensity in the reconstruction model, but we'll also look at the, let's say, possibly a time varying intensity. And this is where the low rank property shows up. So we'll assume here that our flat field now for a one-dimensional detector, that could look something like this. And then you have a time varying intensity. So really what you should be normalizing with is a, instead of just the first column of this matrix or this image here, you should be normalizing by something that is modulated by this time varying intensity, right? So now this focuses on the rank 1 case, but in many cases it would actually also be of interest to look at a low rank extension of what this is right here. But this talk will just focus on the rank 1 case. And so this is of interest when you have a low signal to noise ratio or a time varying intensity of this form. Okay, so this is illustrated here with a problem where you first acquire the first block of measurements over here. Those are basically flat field samples. So you just record the images without an object in the scanner. Then you start acquiring projections of the object from various angles, and then at some point you move the object out of the detector, you get some more flat field samples, and so on, right? So typically what is done is that you take out all these flat field samples, you compute a mean, and you use that to normalize all the projections. And so this is then the measurements when you take out the flat field samples, in this case, the measurements have been acquired with something called golden angle sampling. So instead of just doing small increments in the angle, you take quite large increments. And this is sort of a technique that allows you to stop the experiment once your reconstruction is sufficiently good. If you only have projections from a subset of let's say a full rotation, then you may not be able to get a very good reconstruction. So after we then reorder the projections according to the angle, then we have the flat fields in front, and we have the rest of the projections. So here we would take the flat fields, compute a flat field estimate, and then normalize this sinogram right here. So here's the connection to a matrix completion, because really we would like to know the flat field for every single projection, but we don't have that information, and we may not even have flat field samples in the middle of the experiment. Typically, you only have them in the beginning, and if it's very fancy, maybe you have some at the end as well. So you'd have very limited information if you want to estimate the time varying nature. But we do have essentially some flat field samples outside the object on the edge of the detector. And this is something that can obviously be utilized instead of treating the flat field samples and the other samples separately. So then the extended model now includes basically time, and it includes projection angles here. So we will have detector efficiency and intensity. So we multiply the intensity here by some scalar here, so that models the time variation. And so in matrix form, we can write it in this way. So we basically get here a rank 1 matrix. That's the flat field with the time varying component. And then we have here that U here would be the attenuation image as a matrix. And so we can vectorize that, and we can make a change of variables. It turns out that by making a change of variables here, we introduce some new hat. It can be any positive vector. Then this we'll use this expression here, and we'll have some omega hat here. Again, any positive vector. We plug that into this formulation up here. And then we can move the part here with the exponential function inside the expression over here. And so our extended model now has some arbitrary positive omega and nu here. They'll not be completely arbitrary, but they can be any positive vectors. And then we've turned this into a model here that after the log transformation will be linear in U, V, and W, where V and W will then be related to this low rank matrix up here. Okay, so then the measurement model will be that we assume here that our extended model is the mean of some random variable and a Poisson distributed variable. This is typical for photon counting systems. So then you have this conditional distribution. And really, we're interested in estimating all these quantities, but we'll start with some initial guess of these, these can be basically arbitrary in the model, but we'll start out with some flat field estimate and some estimate of the time varying nature right here. So as I mentioned, we can take all the flat field samples, we can compute nu hat. And we can also sometimes compute this. For example, if we had rows in the sinogram that are just flat field measurements, that will allow us to get some initial guess of the time variation. That may not be possible, but in some cases it is. Then, of course, we can do maximum likelihood estimation. This white bar here, if I go back one slide, that is basically this function right here. And after I take the log of that, I basically get a convex function of my parameters U, V, and W. And I can, of course, extend that with a maximum a posteriori estimation by adding some suitable prior distribution on my model parameters. And so one particularly useful approximation here is if you do a quadratic approximation to this posterior distribution, then you can approximate it by some weighted least squares term where we have this these Kronecker products that model the structure in this rank 1 matrix, right? So the rank 1 matrix is hidden in these two terms right here. And then the B here is just a let's say a normalization by the initial estimated flat fields matrix. So then the basic methodology here is to start out with an estimate of the flat field. Then we compute some estimate of the time varying nature here. And one particularly interesting way of doing that is to use some kind of parameterization. So we'll use some parameterization of this. For example, we could use a linear parameterization or something else. There are, of course, many possibilities, but we may want some kind of smooth approximation using the assumption that the intensity varies slowly. So then using this posterior or approximate posterior, depending on whether we use this quadratic approximation, we can, from a, let's say, Bayesian framework, compute point estimate, for example, maximum a posteriori estimates or posterior mean. And we may also have some set of essentially regularization parameters or model parameters that we may need to put some prior on as well. So the details here are not so important, but basically we can compute all kinds of things once we have this this distribution right here. So I'll end here with some numerical results, and then I'll take some questions afterwards. So here's just an illustration of what the normalization looks like, and then the error in the sinogram. If we do not apply any correction for the time variation, then you see that you have a quite large error. It grows over time here. So this is the projections that are acquired last. If we have projections in the flat field projections in the beginning and in the end, it seems reasonable to use a linear parameterization. So if you compute the time variation using linear regression, you get something like this. But the example here is not based on a linearly varying intensity. So there is still some kind of slowly varying nonlinear change in this direction. Or you may simply use the top rows and bottom columns here to take the average of those and get some estimate that will be noisy. So now you kind of see some stripes in the vertical direction as well. And if we know the exact profile here, this is the error that you get here. So now let's look at what the reconstructions look like. So the first one is filtered back projection, which is really the workhorse here in many experimental communities. So without correction, we see all the rings in the center and some artifacts around the object. It doesn't really help to do linear correction or correct for using the other type of correction. And this is the reconstruction we get if we use the ground truth. And it also has some artifacts or errors that are large around the border of the object. So the second method here is a pre-processing combined with pre-processing. So here it's stripe removal in the sinogram, and you can see that that takes care of most of the rings, but you still have some effects happening around the edge of the object. So then using Markov chain Monte Carlo, you can compute an estimate of a posterior mean, and we do this with the quadratic approximation. So it's an approximate posterior mean in some sense. And as you can see from these reconstructions, they look almost exactly the same. So it doesn't really matter how we initialize the time variation here. So even without so just taking a constant function here as the initialization, we still end up with a reconstruction here that is as good as with better initialization. So it's quite robust to the initialization. And the same goes for the approximate map estimate. So this is another point estimate. They look almost identical here. And we can also look at the errors, and you can see quite clearly that even this pre-processing technique here leaves some rings in the error, or basically they show up in the error images here. So there's quite a big difference here in these, but you still see some errors in the center, and this is exactly where the rings are the most severe, because this is, as I showed earlier, where the intensity of the rings are the largest. So here's a few more results. So here it's based on 100 random realizations of data, where we did reconstructions with these three methods and compute the empirical mean and the width of the 95% credible interval. So this is, of course, some kind of indication of how much the individual pixels in the reconstruction vary for different realizations of the noise. But we can see that that we have the least artifacts, at least on average, in this reconstruction. So there is certainly some bias over here that is due to the let's say model not being able to fully capture the time varying nature of this experiment here. So you can also look at the relative attenuation error. So this is, of course, the error in the reconstruction, and you can see that using the standard filtered back projection is quite a lot worse than using this pre-processing, and that is somewhat worse than using this model that takes both the detector efficiency or response and the time varying nature into account. So the last slide here is about possible extension. So as I mentioned, you could replace this rank 1 matrix here by a low rank matrix, and this is I know of interest in some cases where, for example, you have non-linearities in the detector response, where you seem to be able to model that with low rank matrices. Now we can't apply the same trick to the same change of variables that allow us to include basically get a linear term inside the exponential right here. So now this is actually a much more difficult problem, seemingly much more difficult, and I'm not quite sure how to go about extending the model with this kind of formulation right here. So it seems to be more difficult. So another extension is to apply the same kind of technique to a spectral CT. So this is a case where your intensity, your source has photons at various energy levels. So you have a whole spectrum of incoming energies, and your detector may also have different effectivity or efficiency at different energies. You may still have something that's time varying, and your object here is also then something that depends on the energy. So the attenuation of the X-ray is energy dependent. And this is typically something that can be decomposed as a low rank term, because you typically only have a few different kinds of materials, and that means you can do an expansion here of let's say if you have K materials, then you would get a rank K matrix here out of this in your model. And the last extension here that would have something to do with low rank is that you could apply some kind of prior on the time variation here based on smoothing spline regression, and you can do that by using the so-called spline kernel. And this is a symmetric positive semi-definite matrix that has the property that the lower triangular part of this matrix is actually the lower triangular part of a low rank matrix. And this means that you can store this matrix in if you have n parameters, it's O of n storage, but also you can do computations and factorizations in O as n as well. So this is something that, of course, can easily be combined with this model, because it's just using this parameterization in the model. So just to summarize, this is a new extended reconstruction model that includes the source detector uncertainty. This means that we're jointly estimating a rank 1 matrix and the attenuation image. It's a generalization of many or several existing methods. So it's can be used even where existing methods are used, but where it's particularly useful is when you have low intensity experiments, for example, low dose or fast acquisition, where the intensity is low and the rings these ring artifacts show up as something that severely reduces the quality of the reconstructions. Okay, so that was it. Thanks for listening.
Thank you very much, Martin. So now we are open to questions. Are there any questions? So I have one quick question. So, so your method compared to the previous one, how does it compare with regard with computational complexity? Is the performance different, or?
So let's see. So if you use a model like this, well, you would solve this using some iterative method, and there are many choices. But many of them are variants of some kind of stochastic gradient method, or
so that's what you used?
So here we use, I think, an accelerated gradient method. Of course, it depends on what your prior looks like, whether it's differentiable or non-differentiable, and then of course you need to choose a suitable method. But it's significantly more expensive than using filtered back projection or this grid rag method. but you also get, you can get much better reconstructions in this low noise, signal to noise ratio regime. And also you typically don't need to solve the problems very accurately because there's some inherent regularization in gradient methods for these ill-posed problems. So if you don't have the right regularization, it's typically a good idea to stop the methods before you reach a high accuracy solution, because what you'll see is that the quality of the reconstruction starts to decay a little bit if you get high accuracy. And this is because you're not really solving the right problem if your regularization is not quite correct. And it's a phenomenon called semi-convergence.
Thank you. There's another question in the chat. Amir, do you want to?
Compressed sensing and the number of projections. So this can easily be combined with that. So it doesn't. It's not something that rules that out. So this would be that you reduce the number of projections as a way to reduce the dose, and this has been shown to work quite well. Then you use total variation as a prior to get good reconstructions, basically. But it turns out that when you have this problem with low signal to noise ratio and these ring artifacts, then total variation regularization is not sufficient to get rid of the rings. So you can easily combine this method here, where you're using this model here of the low rank, let's say, detector source model, and combine it with a total variation regularization to apply this method here to compressed sensing, right? So it's complementary in that sense.